All right, so we want to take a moment and look at something related to uh, matrices that is kind of an interesting idea. It gives us some interesting tools, and it's the idea of determinants. Now, a determinant is something it's a value that is found from a square matrix. We only find determinants of square matrices, and that value it shows up and is used in a variety of situations. Let me just give you an example real quick. Let's give you the simplest example um, of how to find the determinant. So if we have a 2 by 2 matrix, A, B, C, D, all right, then the determinant, first of all, we indicate the determinant by taking the matrix name and putting little absolute values around. And so that's the notation for, for the determinant. So when you see that notation, when they say find this right there, they're saying find the determinant of A. And for 2 by 2 matrices, we just have a formula. It's simply AD minus BC. It's this minus this product, that product minus that product. Okay, and that's the determinant. So it's a number, it's a single number that's associated with that matrix. Now, that determinant we've seen before. We've actually seen it as part of the formula for an inverse. It was the part of that where we had 1 over AD minus BC, right? There, that part of the formula. And so we used it there to say that if that is 0, then the matrix does not have an inverse. And in fact, that's going to be the case. That's one of the main uses for determinants, is if the matrix is 0, or if the determinant is 0, then the matrix from which it came does not have an inverse. It's not invertible. Okay, and so if that matrix came from a system of equations, because it doesn't have an inverse, then that system does not have a unique solution. So we start tying these ideas of inverses to solution to solving systems. So in short, if the determinant of the coefficient matrix equals 0, then the linear system of equations does not have a single solution. Now, it still could have 0 solutions. It still could have an infinite number of solutions, but it does not have a single solution. All right. So now, for a 2 by 2 matrix, the determinant is simple. It's that little formula. For a 3 by 3, it's a little more complicated. For larger matrices, it's more complicated. But I guess the first question is, where does this even come from? Both in the 2 by 2 case and in the larger cases. So I just want to show you this because I think it's really important, because sometimes when you see determinants, they just say here is a matrix and here is how you find the determinant, and there you go. But it seems kind of random in that case. All right, but I want to show you where the determinant, where the formulas for determinants come from, and we're just going to do it in the 2 by 2 case. So we're just going to look at a system of equations that is associated with the matrix A, B, C, D. So let's just call this, I don't know, M. And then we have Cx plus dy equals N. All right, so there's our system of equations that is, generates that matrix. So if I wanted to, so again, what we're asking is where do determinants come from? All right. So if I wanted to solve this system right here for x and y, I would do my thing. I would say, okay, let's take a times c, or negative c times row 1, let's do it this way, plus A times row 2. And that will give us a new row 2, right? And so negative C times row 1 looks like this. Negative ACX negative BCY equals negative CM. A times row 2 is ACX plus ADY equals AN. Let's just make sure we didn't do anything wrong. And then we add those together. And look, the ACX terms are gone. That was the whole goal, right? That's the definition. And then we have negative BC, the sum of these two terms, right? And the sum of those two terms is ADY minus BCY equals AN minus CM. I just swapped the order, but I've kept the signs appropriately. Or factoring out a y, AD minus BC equals AN minus CM. Okay, and finally y, the solution we're after, is AN minus CM over AD minus BC. Now what you need to notice is this. Y, the solution to our the y solution to our system is equal to this. And it will only happen, it will only exist if AD minus BC is non-zero, right? Because if that's 0, then this whole thing wipes out and there's no solution. But more importantly, look at that. AD minus BC, AD minus BC. Where do the formulas for determinants come from? They come from solving the system, and at some point you're going to divide in the solving process, and you're going to have a denominator, and that denominator turns out to be the formulas for the determinants for the 2x2 case as well as for larger cases, right? 5x5, the nasty formula for 5x5, it can be found if you really wanted to do it by completing elimination on a 5x5 system and looking at the denominator you get in this last step that you for solving for your first variable. Okay, so in other words, the determinants come from solving the system, okay, and there they are. All right, now thank goodness we don't have to solve the system, because if you can imagine taking a 3x3 matrix and leaving the variables in there, or the coefficients in there as letters, and working your way through all this, it's a big mess, right? So I'll give you easier ways to find the determinant, but I need you to know that the determinant in all cases is the result of solving a system of equations, and it's the denominator of one of the solutions. Okay. All right. So that being said, 2x2 case, pretty easy to find a determinant. All right. So the question we have is, how do we find larger determinants? Now, before we do that, let's dig into. We'll introduce this in the 2x2 case. Let's dig into another use for determinants. All right, we can use determinants to solve systems of equations, and we have something that's called Cramer's rule, not Cosmo-Cramer. This is Cramer with a C. So let's see. We can use Cramer's rule to solve. We'll just do a 2x2 case, but Cramer's rule applies to all sizes of systems. Okay, so here's how it goes. You take your system, and what you do is the first thing you do is you identify the matrix A, which is the coefficient matrix. Let's put it here. A is the coefficient matrix, which is 3, 4, 5, 7. Now, like I said, we're doing Cramer's rule for a 2x2 case, but if this was a 3x3 case or 4x4 case, you would do the same thing. A is the coefficient matrix. Okay, so it would be a 3x3 in that case, but we're going to do the 2x2 case. So once we have A, then we need its determinant. So we know how to do that. We're just going to take the product of this minus the product of that. So 21 minus 20, let's write that down, 21 minus 20 is 1. Okay. Now we need the matrix that we're going to call A sub x. This is the A matrix that we just have right above us, but with the x column replaced. Remember, this is what I refer to as the x column because 3 and the 5 come from the x's. And then this would be the y column. Okay. So A sub x is the A matrix with the x column replaced. So the y column stays the same. It stays 4, 7, but the x column gets replaced by the right-hand side of the system. All right. And so then we go and we find the determinant of A sub x. So it's going to be 14 minus 4 or 10. Okay. Now, the nice thing about Cramer's rule is this. We can start doing this. Well, we'll finish it. I mean, we'll keep going through this. Now we need A sub y. A sub y is the A matrix with the x column the same. Remember, we're using the A matrix. X column is the same, but the y column is replaced with the right-hand side. And we now try to find the determinant of A sub y. So 3 minus 10 is negative 7. Okay. So once you've found those determinants, you are now ready to solve the system. X, the x part of the solution, right? We need an x and we need a y. The x part of the solution is going to be the determinant of A sub x over the determinant of A. So in this case, it's a 10 over a 1 or a 10. The y part of the solution is the determinant of A sub y over determinant of A, which is going to be negative 7 over 1, which is negative 7. And so our solution is 10, negative 7. Okay. So these formulas are universal. It doesn't matter if it's 2 by 2 or 3 by 3 or 4 by 4. X is always A sub x over A. Y is always A sub y over A, the determinants. And then if it was a 3 by 3, you'd have a z term, a third unknown, and that would be the determinant of A sub z over A. So for Cramer's rule, you can use it for all different sizes. You just would have a formula for z. You would also have an A sub z and a determinant of A sub z. And your formula, right, would be A sub z, determinant of A sub z over determinant of A in the 3 by 3 case. And of course, that means you're finding the determinant of 3 by 3 matrices. Okay, so it's kind of interesting that we can use this determinant, this seemingly kind of random jumble of arithmetic computations, to actually solve systems. And you see that it's kind of nice here. One of the nice things about this is I can find, if for some odd reason I just needed to know what y was, I could just jump right to this formula and find y. I wouldn't need to solve for x and then plug it back in and then figure out what y was. I can just find y right away. Okay. All right. So that leaves us. That gives us a nice use of for determinants.